In Chapter 9, we're going to take a look at estimation and confidence intervals. We're going to do point estimation and confidence intervals for one population parameter in this chapter. The parameters we're going to be looking at are the population mean mu and the the population proportion or percentage p. So here we go. First, we need to talk about point estimate. When we talk about the point estimate, we're talking about a single value, one number, one guess at the estimate of the population parameter. So it's one guess, one shot guess at the value of the population parameter. Now, usually we use statistics, remember, the numbers that we get from the sample, in order to estimate the population parameters. So but the idea of point estimation is to use a single number to guess at the value, the unknown of the population parameter. Now, the statistic that we use is known or is called an estimator. Okay, now our estimators are two types. They're either biased or unbiased estimators. The unbiased estimators are those whose center of sampling distribution, remember these estimators are statistics. So these statistics are random variables because they change from sample to sample. So the mean, the center of the probability distribution of these statistics, if it's going to be the parameter, the population we want to estimate, we call that statistic an unbiased estimator. And we would like to have unbiased estimators. So the biased estimators are those whose center of the sampling distribution is not the mean, or it's not the parameter, the population we're trying to estimate. Okay. Now, here's an example. For instance, we're looking at the parameter of the population is the mean, which is our interest in this segment. And the estimator, which is the statistic, is going to be X bar. And according to central limit theorem, the center of the sampling distribution of X bar, mu of X bar, is the mean of the population that we want to estimate. That's mu of X. Therefore, X bar is an unbiased estimator of mu, the population mean. Okay, so that's the idea of unbiased estimators. Now, that's just what that is, a single value. The other form of estimation is the interval estimates. With interval estimation, the idea is to try to capture the parameter, the population, inside an interval rather than guess with a single number. Now, these interval estimates are also known as confidence intervals. So here I have the definition for the confidence interval as a range of values, which is an interval based on point estimate, where parameter is believed to be located in. So that's what a confidence interval is. Now, associated with every confidence interval is a confidence level, and that's what this is. The confidence level tells us how sure, how certain we are that we have captured the unknown of the population, the parameter. Okay, and usually it's expressed as a percentage. You can express it as a decimal, but usually we call it a percentage. And here I have down here the typical confidence levels are 90, 95, and 99. And of course, the higher the confidence level, the better we feel about the interval that contains the value of the population parameter. Okay. So that's what the confidence level is. Now, here in this example, I'm going to give you an example of how this confidence interval works. So in this example, what we've done here, what we're looking at here, actually, we haven't done this. I just grabbed this from another text. So what this example illustrates is the following. here we're looking at, we're trying to estimate mu. See mu here, the population, and this population mean mu is the average selling price of a new mobile home. That's what this mu is. Now, in real life, we don't know what mu is. In this particular example, we happen to know what mu is. Okay, and the reason is because the author pretty much has established that right in here. You see that mu is 65. Remember, typically we don't know that. So, assuming mu is 65, and somehow, for some reason, he knows that, the author knows it. So what we do now is, or what's being done here is that, let's say first sample of size 36 new mobile homes is selected in some location. The average in the first sample is 65.45. It's about $65,000, 450. And the confidence interval is 95.44. The 95.44 is 2 standard deviations, so this is a 95.44% confidence level. Remember, usually we don't go with decimals. We either go 90, 95, 99. So that's going to change later on. But in this particular example, in this very special example, the author is thinking, I'm going to go out 2 deviations and try to capture the mean within 2 deviations. That's why it's 95.44. So look at this confidence interval now. It runs from $63,000 to almost $8,000. And here we have, yes, the question, is the mean inside of this confidence interval? Yes. Remember, the true mean is 65. That's what it is. And it's right there inside of that confidence interval. So it looks like the first confidence interval that runs from low to high end definitely has captured it. And the green dot is actually where the the green dot is where the sample mean is. Okay, the sample mean is, and right here in the middle is where the mean is. So look at, there is a discrepancy. In other words, there is a sampling error here, but the sample mean is pretty close to the population mean, so that's actually not bad. Remember, there's no way out of the sampling error. It's always going to be with us because we are sampling. Okay, so that's the first sample. And then a second sample is drawn. And in the second sample, the estimate is 64. So notice how the sample mean again changes from sample to sample. All of these are almost different. And that's why X bar itself becomes a random variable. So somehow this confidence interval was constructed, so second sample will give you that confidence interval. The third one, this is a confidence interval. Notice the confidence interval themselves change from sample to sample. Now, if you look at the ones that contain mu, $65,000, the first one does, second, third, fourth, all of these, yes, means the mean is in there. Now, down the list, at some point we get 2 right here. We have a no, and that's the only one that doesn't actually contain it. All of the other ones contain it. So 1 out of 20 did not contain it, right? Remember, we have 20 samples, only 1 missed it. And if you look at the confidence interval, it's right here on the side. You see this on the side? The confidence interval actually has missed the mean. The mean is right in here. See? So it falls just outside of the lower limit. Okay, but the point is that it missed it. Now, if, let's say, you and I go out and do this, we're going to get our own confidence intervals, correct? And we don't know if our confidence interval is one of those yeses or it's one of the nos. True? Because again, there's no way of knowing this. In this hypothetical example, it happens that we know the mean is 65. So this is the idea of confidence interval. That means if you build these confidence intervals over and over and over and over forever. In the long run, 95, this is a case where we have 95.44%. 95.4% of these confidence intervals will contain the mean. In this case, 19 out of 20, right, contained it. Now 19 out of 20, that's going to be what, 95%? Right, 19 out of 20, I'm using my calculator, yeah. So 95% contain the true mean. So it's pretty close to 95.44. Okay, so that's the idea of the confidence interval. Again, we just want to clarify this. Now, let's continue on. So with a 95.44, and here what I've done is I've actually drawn the general description of what's going on here. So 95.44 is 2 standard deviation. So the interval actually runs from, what you call it? Let me draw it here. It runs from here to here, right? There, from here to here. That's there. That's the interval. Okay. And that 95.44 is 2 standard deviation again. Now, usually we don't want 95.44, but again, I'm just showing you this. Okay. And in terms of z-score, because I'm going 2 deviation above, 2 deviation below, so down below it is where we have actually the z-scores. Okay, so that the interval again represents 2 deviations above and 2 deviations below the mean. Okay, and also note our random variable here is x bar. Okay, this is x bar. That's what the random variable is. Now, if we go 1 deviation above the mean, 1 deviation below, that's equivalent to a 68% confidence level. If you go 3 deviations above and below, you're doing a 99.7% confidence interval. Or the other way to say it is, if I want to construct a 99.7% confidence interval, this number must be 3. I gotta go 3 deviations, plus means above, minus means below. And this will actually suggest, this is suggesting our formula for confidence interval. So notice in our formula, what's changing are these numbers. The multipliers are changing depending on the confidence level, correct? Now we will see that in a moment. Our formula is actually going to be doing that. It's going to have mu plus or minus a number times sigma x bar. And that number, 1, 2, 3, whatever, depends on the confidence level. Now, 2 things. Typically, remember our confidence levels, I have them up here, are 90, 95, 99. So we're going to stay with those standard scores. And in fact, in Megastat, those are preset in Megastat also, and most softwares. And so that's one thing. And I was going to, the other thing, the second thing is that we're not going to do these formulas by hand. Remember, in this course, they want us to use the software. But we show you the formula for some of the things. This is the one we actually show you the formula. But we're not going to do this by hand. We're going to go to Megastat, and Megastat does this relatively easily. Okay, now here's the general formula for confidence intervals. Now, I've kind of changed it slightly. I added my own here. I have 1 minus alpha 100% confidence level right here. See that? And the z here that the authors of this book have is actually equivalent. It should be z sub alpha over 2, but that's the z that you find depending. See, I have it right here. The z that you see in the formula, that's this z right here. This z depends on the confidence level. Okay, so we're going to actually get this z-score from Megastat. Okay, and let's take a look at an example. Let's say if my confidence level is 95%, that means the 1 minus alpha is 0.95. which means alpha should be 0.5 if you solve for alpha. 1 minus a number is 0.95, the number should be 0.5. That's what alpha is. So alpha is 0.5. And half of that is 0.25, and the z-score that goes with 0.25 from chapter 7 that we did last week's lecture, that z-score is 1.96. And if you want to do it by hand, but Megastat will give us that 1.96 number. So here I made up an example that we do by hand. In this example, let's say we're given sigma is known, sigma is 20, sample size 16, and the sample mean, our point estimate, our estimator of the population mean is 100. And we want to do a 95% confidence interval for mu. So in our formula, we're going to do again x bar plus or minus 1.96 times sigma over root n. And that's this formula that you see up here. We're doing this formula. Okay. Now, let's actually go through that example I made up, more details right in here. So what I did is actually I did 1.96 times 20 divided by square root of 16 is 4. So I got 9.8. Now the plus minus, the way you handle that, once you add 9.8 to 100 and you get 109.8, and the other you subtract, you take away 9.8 from 100, we get 91.2. So we believe the true mean mu is somewhere from here to here. But remember, 95% confidence, 95% certainty level associated with that. Okay, that means 5% of the times this interval is bogus. It doesn't contain the mean, but we will never know that. Now, before we go to Megastat, let's take a look at another idea here. Well, the question might be, okay, well, if I'm using x bar to estimate mu, how precise is this estimator? Well, we gauge the measure of how precise the estimator is, how accurate it is, using what we call the margin of error. Okay, so what is the margin of error? The margin of error is the maximum error possible that we make when we use x bar to estimate mu. So for example, if I estimate the average parcel at on a UPS truck weighs 12 pounds. That estimate of 12 pounds could be off by, let's say, no more than 2 pounds. That's my margin of error. It's the maximum error of your estimator. Okay. Now the margin of error is also known as sampling, as just error, not sampling error. It's simply error. They just call it error. Okay. And again, it's the absolute value. That means it could be plus or minus. Okay. Now, here's our formula again for how do I actually measure the margin of error. What's to the right of plus or minus? Right here. What's to the right of plus or minus? That's what margin of error is. It's when you multiply z times sigma divided by square root of n. That's what your error is, or margin of error. Okay, it's pretty easy. Now, in general, as the error increases, it's not a good thing, right? Remember, that's a measure of precision, the precision of estimator. So as the error goes up, means your precision is going down. And if the error goes down, means your precision is going higher. Now, and we can also relate a margin of error to the length of the confidence interval. The length of the confidence interval is the distance from low to high end. So if x bar is at the center of this interval, then E, there you go, to the right is E and to the left is E. So for the right upper limit of the confidence interval, we do x bar plus E. For the lower confidence limit, we use x bar minus E. The whole length is therefore E, and E makes 2E, correct? I'm looking at here. E and E, those make up the whole length, which is L. So I have written this information. Megastat calls the margin of error the half interval. So this is actually going to help us understand what does a half length mean. Remember, the half length, that's L over 2. This is half length. Half length means margin of error. Keep that in mind, please, as we go through Megastat, because it's going to show up on the output. Half length is margin of error. Okay. Now, the next question might be, is this, well, how large of a sample do I really need in order to estimate mu? Well, the answer to that comes from the margin of error. So here I have the formula for margin of error. Okay, and there it is, right down here. Now, in this formula, if I solve it for n, so if you follow the algebra, that's fine. If not, that's fine too. What I've done is I multiply both sides by square root of n, so it appears on the left now, and I lose it on the right because it cancels with the denominator here. And then I squared both sides in order to lose the radical. And then I divided both sides by e squared, and there's our formula for sample size. Megastat actually gives you this, but I just want to illustrate that through the use of the formula. Now, for sample size calculations, if we do it by hand, we always round up. But again, we use Megastat, so you need not worry about it. And here's an example of rounding. Let's say n is 23.15. We're going to round it up to 24. Notice we do not follow the usual rounding convention. 23.15 in ordinary math classes are rounded to the nearest whole number as 23, right? Because 0.15 is closer to 23 than it is to 24. But in statistics, because of sample size, we cannot have portion of a person or a subject. So we always round up in order to have a better estimates. If the sample size is, for example, 18.76, that naturally rounds up. But even if it's not, any decimal, regardless of what's in the 10th position, you always round up. Okay? The only time you don't round up is when actually the number itself is going to be a whole number. Now here's an example. That's how the question is. How large a sample do we need to estimate mu if we want to be 95% confident in our estimation with a margin of error of no more than 30 units? Let me put a question mark here. Okay, so that's what we want to know. How large a sample do we need? And there's our question mark. Okay, and we're going to assume sigma is 190. I'm just making these up. So I went ahead and plugged in the numbers. For 95%, alpha is 5, half of that 2.5 is 0.251.96. Again, this we got it last week in chapter 7, near the end of chapter 7. And you just plug in the numbers and we get this one. But Megastat will do this for us also. So I need a sample of size 155. If I want to estimate the mean with this much accuracy, 95% with that, not accuracy, with that much confidence, I should say. Okay, our accuracy is right here, to within 30 units of the actual value of the mean. Okay, now, what if sigma is known? It's unknown actually, because in our formula we assume sigma was known. See, when I go up here, sigma is known in our formula right here. See, sigma is known. What if we don't know sigma, the population standard deviation? Well, if we don't know the population standard deviation, then what we do is we actually replace it with S, the sample standard deviation. It's point estimator. That actually changes the formula slightly for the confidence interval. Instead of what used to be a Z, we now use a T. Okay. Now, this T is actually a T probability distribution, which is called a student's T distribution, or simply a T distribution. This probability distribution looks just like a normal distribution. In fact, in this drawing, what I'm showing you is 3 curves. One of them is our standard normal curve. Okay, that's what one of them is. And that's standard normal curve is the one on the outermost curve is a standard normal. Inside the blue is the one with df1, and between the green and the blue is another T curve with df6. Now df here stands for degrees of freedom. Now, the degrees of freedom, the gentleman that actually discovered this distribution, his name was William Silly Gossett. And he's the one who called the parameter of the T distribution its degrees of freedom. So that's where it's getting its name from. All the degrees of freedom tells you is how to draw the curve. Basically, that's all the degrees of freedom indicates. And of course, the software, once passed on to the software, then the software knows how to actually draw this curve. Now, these are some of the basic properties of the T curve or T distribution. First, because it's probability distribution, so the total area under the T curve must be 1. And a T curve goes just like a normal distribution. It goes indefinitely in both directions, upper and lower tail. In both of these, it goes forever to the right and it goes forever to the left. Right, this is the left, it goes forever to the left. And of course, it's symmetric about 0. A T distribution has always center 0. And this is what we call actually a central T distribution. That's why it centers at 0, central. It is possible for a T distribution to be centered other than 0, but in this course, all our T distributions are centered at 0. It is symmetric. Mean, median, mode are the same, and 50% of the areas to the right, 50% to the left, just like the normal was. Now, the degrees of freedom, as they increase, the T curve becomes just like a standard normal curve. Okay, and that's what, again, the curve on the outside is. That's a standard normal. Remember, standard normal is normal 0, 1, right? That's N0, 1. That's what the standard normal is. Okay. And so those are the characteristics of the T distribution. All right, now how are we going to use this actually in our work? Well, in our formula for, and here by the way I have other T distributions. I got this image, I copied it from Wikipedia. In Wikipedia, the actually degrees of freedom here is indicated by Greek letter, looks like italicized V, but that's actually NU. Nu, Greek letter nu. We already know what mu is, right? Remember, mu is this one. So this is another Greek letter. So again, it illustrates what the other image was showing, the curves that were showing up there. Okay, the ones I have here, see, it's kind of like this one. Now, here degrees of freedom is 1, is this with golden curve. Then degrees of freedom is 2, that's the next one up. Degrees of freedom 5 is the next higher up. And degrees of freedom infinity, with infinity means very large. And that's what this says right here, property 4. As degrees of freedom becomes large. Well, how large? There you go, infinity, large. Then the outermost curve is the standard normal distribution. So that's what this one is. Let me actually show you. So this curve, this one that you're looking at, this one on the outside is normal 0 and 1. You see that? And there we have it. So this is just the T curve. So in our formula, what was x bar plus minus z sigma over root n? So it's now going to be what you're seeing here, right there. See that? That's our formula. Our formula is now x bar plus or minus a t times, we don't know sigma, so I'm going to put s over root n. And here s is the sample standard deviation. The numerator is the sample standard deviation. Okay? StatCrunch will give us all of these. Alright, now here's something interesting. The assumptions that we have about the confidence intervals is that our sample is a simple random sample, and we are sampling from a normal population or large samples. Now, in the eyes of the central limit theorem, remember how large was large? N greater than or equal to 30. So that's going to be considered large for us when sample size is 30 or more. Okay? And of course, sigma is unknown. Okay? And here we have it. So our confidence level is 1 minus alpha. Now here, don't worry about the use table. We don't use that. To find this, we're going to use StatCrunch. We're going to use Megastat. Okay. And degrees of freedom is n minus 1 right here. The degrees of freedom help us go to would be a table, but we're not going to do that. So don't worry about our degrees of freedom here. And we have the formula, right? This is our formula. And those are the step-by-step how to do it. Now this confidence interval, it will be exact if you sample from normal population, and it's approximately only approximate for large samples and the non-normal populations. Now the t is pretty robust, so the interval is a robust interval, means the moderate departures from normality, no problem. This thing still works. Okay, now we have reached our first example that we're going to use in Megastat. Okay, so let me do this. Let me enlarge this so we can see it a little better. Okay, so in this example, and this is in your book, the question reads: a research firm surveyed 49 randomly selected Americans, so that 49 is a sample size, right? To determine the mean amount spent on coffee during 1 week. The sample mean was $20 a week. The population distribution is normal with the standard deviation of $5. So here sigma is known, right? Sigma is known. So that means in this example again, sigma is going to be, let me write that, sigma is $5. It's known. Okay. In part A, what is the point estimate of the population mean? That's pretty generic question. In general, the point estimation of population mean is the sample mean. And it says explain what it indicates. It just indicates what a point estimate, a single value, a guess at the value of unknown population parameter. In this case, $20 a week is our best guess at how much the true average spending on coffee during 1 week is. Okay, for Americans. This is for Americans, not, let's say, for Russians or for Chinese or whatever nationality. Okay, so let's actually now, we're going to go to Megastat. So I'm going to pause this. You're not going to notice a difference. I'm going to pause this. I'm going to leave my note and go to Megastat. So let's take a look at Megastat and how we're going to answer this question. Okay, so now I am in Excel. Now I've already have installed Megastat. I'm sure all of you have already done that. And here's my add-ins. So I'm clicking on add-ins. Megastat appears. Click on Megastat. This is the step-by-step in Megastat on how to do this. Okay. So in our example, the sample size is 49 with other information. So first I need to go down here confidence intervals, and click on that, left click once. Now pretty busy pop-up, right? So right on top it says confidence interval for the mean, below it is confidence interval for P. Well, that's population percentage. We're doing it for the mean. So see, when I click on these, the dialog box changes, right? So make sure you click on the top one. We're doing this for the mean. Now there's a mean here and there's a mean here. This box that's waiting for a response here, this is actually the sample mean. Okay, so I'm going to input the sample mean of 20. There you go. And the standard deviation, the known deviation was $5 a week, and the sample size was 49. That's it. Now if you look at here, see your confidence levels are preset 90, 95, 99. What if, let's say, the question said do in 92%? That's no biggie. You just type in 92, and there you have it. That's your confidence level. Now I'm going to go back to our confidence level was 95%. So there you go. You can also put a decimal. It says select a value or put your own. Now here we're going to see you have a choice of a Z or a T. We're doing a Z interval because sigma is known. Remember, sigma is known. That's how you say, well, which one do I use? When do I use which one? If sigma is known, you use Z. If sigma is unknown, you use a T. Okay? And you can actually preview the confidence interval here. There you go. That's it. So on average, Americans spend $18.6 to $21.40 a week on coffee. Okay. Now, if you hit OK, it's going to actually print it right here for you. And remember, this is now in Excel. So everything of Excel's functionalities at your disposal now. So you can highlight this if you want, jazz it up, merge cells, whatever you want to do. There you go. I'm just going to highlight it. Boom. There you have it. So we did a 95% confidence interval. The mean was 20, deviation 5, sample size 4. And here's a z-score, 1.96. Where did that come from? That's, remember, alpha was 0.5 for the 95%. Alpha is 0.5. It's the other part that makes it 100%. A z, and then you half that. You divide it by 2. So 0.5 by 2 is 0.025, and a z of that is 1.96. This is like would be a table value. That's what that is. And here's a half width. Remember what the half width was? If you double click, the cell is activated. Half width means what? Margin of error. So there you go. If the question asks what is the margin of error, that's what that is, 1.4. And here is the upper and there's the lower confidence limits. Goes from 18.6 to 21.4. Okay, so that's going to be the answer to our exercise. So I'm going to go ahead and go back and answer the question now in my note. Alright, so let me transfer those numbers from Megastat. We found this to be, let me actually use this color. Okay, so from Megastat our answer is going to be from 18.6 to 21.4. That's our confidence interval. Okay, and that answers part B. Now it says explain what it indicates, means interpret that confidence interval. That means, no, this says that we are 95% confidence that the true average amount spent by Americans on coffee during 1 week is somewhere from $18.60 to $21.40. That's the interpretation. Okay, So again, for this one, we used, let's call this a Z interval procedure is what we used. Now, in our next example, we're actually going to use a T interval procedure. So let's read on with this one before we actually see some of the answers. So let's begin this next example. The U.S. dairy industry wants to estimate the mean yearly milk consumption. A sample of 16 people reveals the mean yearly consumption to be 45 gallons with a standard deviation of 20 gallons. Assume the population distribution is normal. In part A, what is the value of the population mean? Well, nothing in here that I read indicates what the population mean is, right? We have a mean yearly consumption, but that came from a sample of 16 people, didn't it? Right? And in fact, right up here, we say we want to estimate the mean. So, what is the value of population mean? It's unknown. We don't know. What is the best estimate of this value? The best estimate, our estimator, is the sample mean, which is 45 gallons. Okay. So there you go. In part A, mu is unknown. The best estimate of it is x bar. In part B, explain why we need to use t distribution. What assumption do you need to make? Remember, whether we use a z or t depends on whether we know sigma or not. Here we were told nothing about sigma being known. If you go back to our exercise that we just did, you see up here it says a standard deviation of 5. We're going to assume, there you go, population is this with a deviation of 5. That means this is a population deviation. So we're not told that down here. So in part B, explain what we need to use. Why? It's because sigma is unknown. If sigma is unknown, we use a t distribution. What assumption do you need to make? Again, the assumption is normality, which we have here. Assume population distribution is normal and sigma is unknown. And both of those together give us a t interval procedure. In part C, what is margin of error? Well, right now I'm just giving a generic margin of error because in order to determine the actual numbers, we need a confidence level. We need to construct a confidence interval, then determine the margin of error. So I'll do that after we do the confidence interval. But at this point, the best we can do for part C, margin of error is t times s over root n. Now in part D, it's asking us for a 90% confidence interval. And it says, okay, parts D and E we're going to get from megastat. Okay, because once we run a 90% confidence interval, it will give us a t value. Okay, the reason they're out of order here is because the book assumes you're going to do this by hand. In order to do part E, you need to do part D first if you do this by hand. That's why I have part D and E are going to go to megastat. So again, I'm going to pause this and we're going to go to megastat. Okay, so remember, x bar is 45, sample size 16, and standard deviation is 20. Our confidence level is 90%. So let's go to megastat in Excel. Okay, so now I'm in Excel and I go again, add-ins, and the megastat confidence interval. Again, this is a step-by-step. That's all the step there is. There's nothing else to this. And so we're doing exactly like before. Instead of the mean, now this time in this exercise, again, the sample mean was 45, correct? So I'm just going to type 45. And then the standard deviation turned out to be from the sample 20. Our sample size was 16. It's rather small. Our confidence level is 90. And our cells, we got to click on or check the T, that radio button. Make sure you click on that T because sigma is unknown. If you preview the interval, you see it right in here. If you hit OK, you get more information. So, a 90% confidence level with these given. The T, remember in part D of the exercise, it says, what's your T score? This is the answer to that. T is 1.753. The degrees of freedom, df, is sample size minus 115. So Megastat is saying that it's found this T score using the 15 degrees of freedom and based on 90% confidence level. Notice what I did is I double clicked in this cell and it shows you more decimals if you need to see. The half width, remember our half width is what? Margin of error, correct? ME. So the question, if margin of error was asked, the answer to margin of error is 8.765. And the upper lower confidence limits are from 36 to 54 almost. 36 to 54. So now I'm going to go back to my note and carry these scores for upper lower confidence limits into my note. Okay, I'm back and here we go. So again, the answer to part D from Megastat are T. I need to write this down now. Okay, let me do that. So our T is going to be 1.753, and in part E, develop the confidence interval 90%. Confidence interval turned out to be 36.24. I'm rounding the number to 53.77. That's what that turned out to be. In part F now, would it be reasonable to conclude the population mean is 48 gallons? Okay, well, as long as 48 gallon is inside of this confidence interval, then it's reasonable because we expect it to be in there, right? So as long as whatever score they give you in part F is inside the interval, it's reasonable. Any number inside the interval is reasonable. So the answer is yes, because 48 is inside the confidence interval. See how that worked? And there you go. We did this entirely in in Megastat, and we did it step by step. The last thing we want to do here is we're going to look at confidence interval for proportions now. Now the word proportion here also means percentage, by the way, or rate. Percentage. Okay, so proportions become percentages. So the population proportion is like capital P, and that's capital X over capital N. What are the X and N here? X is the number of subjects, items, objects having the attribute or characteristic that we're looking for, and cap N is the population size. Now here the percentage, these are a few examples of percentages. Percentage of US adults who have health insurance. Percentage of cars in the US that are imports. Percentage of US adults who favor stricter clean air health standards, and percentage of Canadian women in the labor force. So there you go, any percentage you can think of. And here's a formula that your book gives you. Okay, so again, be careful with the capital P here. This capital P is for population percentage. Okay, population percentage. This P is like there, little p is sample percentage. That's what that is. Okay, so just want to clarify that for you. Now, again, we're going to use Megastat. So let's take a look at this exercise. In this exercise, It reads, Netflix is considering a new rom-com, that is romantic comedy, series. Before making a final decision, the producers design an experiment to estimate the percentage of viewers who would watch the series, the new series. A random sample of 400 viewers was selected and asked to watch the first 2 episodes. After viewing the episodes, 250 viewers indicated they would watch the new series. Okay, so in part A, we want to know the estimate of the value of the population proportion of people who would watch the new series. Okay, so notice from a sample size 400, we are inferring to the population of all viewers, including you and myself. Okay, so an estimate of the value of the proportion. Well, the little p is an estimate of capital P. In other words, the sample percentage is an estimate, a best guess at the population percentage. That's what we think. So we need to calculate what the sample percentage, correct? And that's what I did. Little x over little n. 250 said they would watch it out of 400. That's 62 and a half. 62 and a half. Almost 2 out of 3 said they watch it. In part B, develop a 99% confidence interval. That's part B is hanging on. And part C is actually the interpretation. Okay, so to do part B, I need to go to Megastat. Okay, so I'm in Megastat now. I'm actually in Excel now. I'm going to click on add-ins and look at Megastat. Okay, let's go to confidence intervals. Click. And this time we're doing percentages, so I'm going to use the second, not the first, the second entry. Click on that. Now in here it says what is P. P is that 62.5% that we found, but you don't need to actually put that number in. The easiest way is to actually put the number of people that said they watch the new series. Now if you put a number here that exceeds 1 or more, the software will change that to X. Remember, the formula is P, little p, X over N. So look what happens. I'm just going to type to check out the P. See, it changed to an X. So now Megastat knows, oh, okay, so that's the number of successes. It's not a percentage anymore. And the sample size is 400. Our confidence level for this one was 99. Again, preview. Here's the answer to the exercise. If you hit OK, this is the confidence interval for proportion. Again, the things you put in. That's your 62.5%. This time the z-score is 2.576. That means, okay, alpha is 1%, right? The other part that makes this into 100%. Our uncertainty level is 1%. That's 0.1. Half of 0.1 is 0.005. A z of 0.005 is 2.576. Now here's your half width or margin of error, 6%. And this is the actual upper lower confidence limits, 56% to 69%. So we estimate with 99% confidence, that's pretty high confidence, anywhere between 56 to 69% would watch the new series. So I'm going to go back to my note and transfer these numbers to my note. Okay, and here we are. So let me actually type or write these numbers from Megastat. The number was 0.563 all the way to 0.687. There you go, 0.687. Okay, And we got the confidence interval. So let me just put ME, margin of error, is 0.62. Now here's the interpretation of this margin of error. When we say 62.5% of people in the population will watch this new series, that estimate of 62.5% is off by no more than 6%. That's the maximum error of the estimate, is 0.66%. That's what that is. Okay. And in part C, it says interpret your findings. And here's the findings. We are 99% confident in the true percentage of those who will watch the new series is somewhere from 56.3% to 68.7% with a margin of error of 6%. And that is how you do confidence interval for percentages. So with that, we are done with this chapter. So again, in this chapter, we learned how to use Megastat to construct confidence intervals for population mean and for population percentage or proportions. And that concludes chapter 9 for us.